All right, welcome back. CSE 215, Discrete Structures, Lecture 2A. So, one thing we're going to do a lot of is create new sets from old sets. And so here's an example of how we can create a set from a given set. This is something called the power set. And I'll write this as sort of the script P of S. So the power set of a set S equals the set consisting of, well, a set is a collection of things. What are the things in this power set? They're all the subsets of the set S. So the power set of S is the collection of all subsets of S. Okay, so an example will help here. Suppose S is the set consisting of two elements, the number 1 and the number 2. What are the possible subsets of S? Well, we know the empty set is always a subset, and we know the set itself is a subset, right? S is always a subset of S. Are there any other subsets? Well, a subset is simply a collection of things where each thing belongs to the original set S. So in fact, there's two other subsets. They're both singleton sets, the set consisting of just the element 1 and the set consisting of just the element 2. So the power set of S is a set containing four things: the empty set, the singleton 1, the singleton 2, and the original set containing 1 and 2. Now think about this for a few seconds, right? We have a set containing four other sets. That might be a little weird, but it's again, we have to kind of detach and not try to think too deeply about this, right? It's just a set consisting of four things: 1, 2, 3, 4. Each of those things happens to be a set, and this set happens to contain two things, and this is the weird set that contains nothing. But that doesn't really matter, right? It's really just a set of four things: 1, 2, 3, 4. Okay, but it turns out each of those things is a subset of our original set S, and it is precisely the collection of all possible subsets of S. Okay, so suppose that T is a set just containing a box. It's a set consisting of one thing. So what does the power set of T look like? Well, again, it's going to contain the empty set, and it's going to contain the set T itself. But that's it. There's no other possible subsets of this. All right. We have a notation for sets that have a finite number of elements in them, which is what we'll mostly stick with for the next few minutes. We can write this symbol. We call this the cardinality of S. And it equals the number of elements in S. And this is only if S is finite, meaning it contains a finite number of things. So when we talk about the cardinality of the integers, right, it doesn't mean the number of things in that set, because there's an infinite number of things in the set. But for finite sets, sets containing a finite number of things, this just means the number of elements in the set. And so we have a property that you might be thinking about with power sets. Here we had a set with two elements. The power set contained four elements. Here was a set with one element. The power set contained two. If we looked at the power set of a set of three elements, it's going to contain the following. And I claim those are the only possible subsets of this set A, B, C. And there's 1, 2, 3, 4, 5, 6, 7, 8. So one element, power set has 2. 2 elements, power set has 4. 3 elements, power set has 8. And there's a pattern here. If we were to look at a set of 4 elements, its power set would contain 16 elements. So we have a fact here which we will touch on multiple times during this course. So for a finite set S, the cardinality of the power set of S is equal to 2 raised to the cardinality of S. And again, this is for S being a finite set. So that'll be useful and arguably interesting down the road. Let's look at the other end of things with power sets, though. The power set is defined for any set. So what is the power set of the empty set? Well, it's going to be a set, and it's going to contain all the subsets of this set here. Well, there's only one subset of the empty set, and that's the empty set. So the power set of the empty set is this thing. Well, the cardinality of the empty set is 0. It has no elements. But what's the cardinality of the power set of the empty set? How many elements are in this set? Exactly 1. This thing right here. So again, the cardinality of the power set is equal to 2 raised to the cardinality of the set. 2 to the 0 is equal to 1. So this formula still holds. And it's important to note that this is not the same as this. This is an empty set. It contains no elements. This is not an empty set. It contains 1 element. This thing right here, this thing which happens to be the empty set, but it contains 1 thing. Now, if you want to have some fun, cardinality of this thing, this set consisting of 1 element, well, since this has 1 element, the power set should contain 2 to the 1, which is 2 elements. What are the 2 elements? What are the 2 subsets of this set here? The empty set, which is always a subset, and the set itself, which is always a subset. And that's it. And this set is different from this set, which is different from this set. And we can go off the deep end with this. We can start doing all kinds of crazy derivations just by taking power sets of the empty set and so on. We won't go there right now, but we may come back to that later. All right, so let's talk about Cartesian products. So a Cartesian product is another way to create new sets from old sets. So to talk about Cartesian products, we need to talk about an ordered tuple. So an ordered tuple is an ordered collection of things, and we can talk about an ordered n-tuple, which is an ordered set of n items. But it's ordered. It's not a regular set. It's a set where we've imposed some ordering. So an ordered 2-tuple, like 1 comma 2, will be different from 2 comma 1. Okay, the order is going to be significant. So set of n items, for example, A1, A2, up through AN. And we draw these in parentheses instead of curly brackets to make it clear that it's not a regular set. It's an ordered set, or an n-tuple. So 2 n-tuples are equal if and only if they have the same elements in the same order. So here's a 2-tuple, here's a different 2-tuple, okay? Different order to the elements, even though they both have a 1 and a 2, they're not the same tuple. Okay, so now we can define our Cartesian product. So A cross B, or the Cartesian product of A and B, is a collection of tuples containing 2 elements, A, B, such that A is an element of A and B is an element of B. Okay, so for example, suppose A consists of the elements 1 and 3, and B consists of the elements C, A, and T. So A cross B will be a set of tuples where the first element comes from A and the second element comes from B. So for example, it would contain 1 comma C. It would also contain 3 comma C, 1 comma A, 3 comma A, 1 comma T, and 3 comma T. And those are the only tuples we can form where we take the first element from A and the second element from B. And you may notice here that the cardinality of A Cartesian product B is exactly the same as the cardinality of A multiplied by the cardinality of B. And again, this is assuming that A and B are finite. So infinite sets, we can still take the Cartesian product, but this nice rule doesn't apply. Another thing to note is that in general, Cartesian product of A with B is not the same as the Cartesian product of B with A. Why? Well, if I look at B cross A, it's the set of tuples where the first element comes from B and the second element comes from A. And just looking at the first element, C comma 1, that's not a member of A cross B, right? So that right there, without even filling out the rest of these elements, tells us A cross B is not equal to B cross A in this case. All right, so next video we're going to talk about set operations, other ways that we can take sets and combine them to come up with new sets.